So all my machines have linkages and mechanisms of some sort inside them. The water clock's actually stuffed full of them, and I'll look at how they work later on in the video. Linkages and mechanisms are a big subject though, so this video is mainly my own experience of making and using them. But I thought probably ought to start with just the basics. So here's the chapter list in case you want to jump to a particular section of the video. I'm going to start with a simple lever. This is the pivot, and if I put a weight on it, it's a 2 kilogram weight, put it on this white mark, at 100 millimeters from the pivot. So to start with, you can see that my arm is moving a lot further than the weight moves. It's 4 times as far away from the pivot as the weight, and so it's moving 4 times further. But also I have to use much less force than if I was moving the weight directly. So if I put a spring balance on the end here, I'm lifting with a force of about 750 grams. Well, part of that's actually the weight of the lever, so wait a minute, take that off. Yeah, that's 200 grams. So I'm lifting with a force of about 500 grams, half a kilogram. So it's the same ratio. It's I'm lifting with 4 times less effort than if I was lifting the weight itself. Wonderful thing, levers. And actually, a lot of hand tools have them. So a spectacular example is my shear. So the handle on the shear is about 1.2 meters, 4 foot. And if I move it a foot, the actual jaws, at the tip of the jaws, move about 10 mil, 3/8 of an inch. So there's a big leverage, if you like, or mechanical advantage. So these shears, they'll easily cut 3 mil plate. I'll just put a bit in here. I can probably do that single-handed actually. Of course, not all tools need such extreme leverage. My cut-off saw, the pivot is down here, and the distance from the pivot to the blade is about 140, and the distance from the pivot to the tip of the handle is about 470. It's very roughly 3 to 1. So I pulling down here will apply 3 times more force on the blade there. Of course, ordinary pliers and side cutters are the same too. And talking about levers, I just had to include the crowbar, a brilliant tool. So this is about the heaviest machine in my workshop, weighs about 700 kilograms. And yet I can put the crowbar under 1 foot and lift it up really quite easily. I can't lift it a long way, of course, but that doesn't really matter, because what you do, you lift it. Hang on, I need to just get my foot in the right place. You lift it, and then you can get a block in, and then you can sort of reposition to get another bite. So I'll see if I can get a second block in. Like that. And then, you know, I could put the crowbar on another block and carry on and get higher and higher and higher. And get it on rollers or get it on skates to move it around. And it doesn't take very long either. Just a brilliant tool. And of course, in this case, the pivot is the ball under here where it rests on the ground. course, actually the whole folder is just a simple lever, really. The wheel is a sort of vice that clamps metal in the jaws, and then the arm bends the metal. Once you start combining levers together to form linkages, they become much more versatile. The maths gets complicated, so I tend to just use bits of cardboard and drawing pins to work it out in 2D. Just two levers together can do a lot. This is actually the model of an arm of a digger, and the rams for this digger go in here, and the sort of range of movements that you can get is quite extraordinary, really. Of course, it's all very carefully designed to give the digger the maximum amount of reach and the maximum amount of power near the ends of the strokes of the rams. Well, this particular digger is the one that's in the local scrapyard and has a claw on the end. So I'll try and fit the claw on. Now this linkage is a lot more complicated. So linkages can very quickly get complicated, but my goodness, it's incredibly versatile. It's a joy to watch it work. I should probably admit that I love diggers. I could happily watch them for hours. Their ingenious design, combined with their precise control and amazing speed, is just amazing. I've left this quite long. The linkages really are worth looking at closely. It's my friend Graham in the cab, wearing his cowboy hat. It's as if the claw is just an extension of his own hand, really. Graham's older than me, and he now has real trouble walking. But once he gets in the cab, he's like a teenager again. These car engines weigh several hundredweight, but you know, he just tosses them around as if they're nothing. So once he's got the whole cars in, he gets the digger sort of above the skip to give maximum power to squash them down as hard as he can to get as much on the skip as possible. The actual clock hands are a bit of a cheat really, they're electrical. There's a motor in the box up there. On the quarter, another motor opens the valve, and then the actual performance is all powered by water. So first thing that happens is water pours through this tube into this can here, and water's quite heavy, so there's quite a big force by the time this can's nearly full. And then once it is full, it tips this lever up here and the longer lever down the bottom, which has attached to the flowers. And as it's quite a long lever, the motion of the flowers is pretty near vertical. Meanwhile, up the top here, there are two smaller cans that fill with water, and they're balanced so that when they get full, they just overbalance. The weight makes them tip over and dip out all the water. And they have these levers on the side connected to another lever that pulls the figure out of the bath. So, and in addition to that, there's an extra little lever in there that rotates a tap to make the water come out of their mouths. So you got all that going on, and then for the finale, what I should have said is that as the flowers pop up, there's an extra lever around the back here that moves this hose, so it moves it from one side to the other. So instead of the water coming down here, it goes into the can at the back there. So that can starts getting heavy, and when that's almost full, that's enough to overbalance this lever here and finally make the trousers drop. And of course there's yet another lever connected to a tap to make them start spinning at the same time. Well, that's about it really, but a lot of levers. So although you could design a basic linkage with cardboard drawing pins, converting it into a 3D thing isn't exactly the same. So this is a 3D version of that linkage, and for a start the weight of the levers was making it not behave in an identical way. It's also quite wobbly. I've just used very basic, just a nut and a bolt for each of the joints. But even with these very simple nut and bolt joints, you can do quite a lot to improve them. So if I just undo this one, well, for a start it's good to have a washer in between. You get less friction that way. Then a washer on the outside, and then you get these special nuts called nylocks. You can see there's a little bit of blue nylon crimped in the end there, and what they do is they just they stiffen up the nut so that it won't just work loose as an ordinary nut would do, used in this way. So then I just tightened up as much as I can, and then just slacken it off by a little bit, and then you've got really quite a stiff joint. Then the rest of the mechanism is still wobbly, but this particular bit is working much better. Other things you can do, I quite often weld a pin to one end of a linkage, so at least the pin is now rigid. Then I sometimes just use one of these push fit fasteners. Just push it over. You have to be careful not to crimp it too hard together. Yeah, it's not too bad now, and that's a reasonable joint. The drawback of these push-fit fasteners is that they're very hard to remove without damaging either the shaft or the fastener itself. So if I do have to remove one, I usually just grind it off. And fit a new one. But for a larger node, the ends of the levers need to have some width to spread the load. This makes them much more rigid and long-lasting. You could do this in many ways. I just welded 2 bits of plate on there. When I'm making prototypes, I very often just use wood hinges just to try something out. But they have that same sort of rigidity that is so useful. Then of course you can buy clevises, these nice little things for the ends of linkages. And the pins have these spring clips that clip over the thing like that. One disadvantage of a standard clevis, if you want a sharp angle, that's as sharp as you're going to get with a standard clevis. But there are also these long arm clevises, which I like a lot, and they can go right back to there, and I find very often that they work better. Oh, you can also get tiny clevises for radio controlled planes. They're great because they're so slender that way, and they just spring apart to go over the steel. Then for sometimes when you want a joint to be able to have some flexibility, I find little ball joints useful. They come in a variety of different sizes, and even again little tiny ones. These are mainly for radio control, the steering on radio controlled cars, but I like them. And then for larger loads, often the best end to a linkage is a rose bearing. Beautiful things, and they come in a vast range of sizes as well. I generally try to avoid complicated linkages on my machines on the principle of keep it simple, stupid, KISS technology. Complicated linkages like this lazy tong pop riveter, any slight play or slackness kind of gets exaggerated through the thing. It doesn't matter on the pop riveter, but if, like as I often might be wanting to do, to use it the other way around, to use a small movement to get the long movement at the end, you end up with something that's really quite sort of wobbly. Of course, it wouldn't matter in all occasions, but they're difficult to design well. I've never actually used one on a machine for that reason. But one addition to linkages that I do find really useful and use a lot are cranks. And so I'm going to talk quite a bit about cranks now. I'll start with bell cranks. They're called bell cranks because they were traditionally used in grand houses for the lordly to summon the servants. So in the smoking room or wherever, the lordly would have a lever like this, and the cable would snake for miles between the walls and the floors until it eventually reached the servants' quarters. The cable would snake for miles and miles, changing direction with these bell cranks along the way, and eventually get to a bell in the servants' quarters. I was given some years ago, and so this seemed the perfect excuse to try them out. It took some head scratching to align the bell cranks to get them to do what I wanted, because if you think about it, all the cables have to be in tension, otherwise it would be very, very heavy. So there's a different sort of linkage that's also widely used in aircraft to reduce the weight. The bell cranks themselves are rather beautiful. They're well made. The pivot goes through bearings on both sides. Of course, you know, in a big house, the cranks, there probably could easily have been more than 12 cranks en route from the posh rooms to the servants' quarters. So the whole system had to be quite friction free and carefully designed to be able to ring the bell at the far end. The ones I got obviously came from quite a big house, because I had one or two of these that had 4 cranks on a single lever arm, so at least 4 posh rooms connected. Down in the servants' quarters, the bells were all labelled so they knew which room to go to. Today, bell cranks are much less posh. You can get bell cranks for model planes to connect the servos in the fuselage to the controls on the wings. Yeah, they're fun to play with. But the sort of crank that I use much more often than any other sort is a crank connected to a motor. So here's my lever or my linkage. Let's put a bolt through the crank, a couple of washers, and a nut on the end. And then we have the linkage powered by the crank. This is a useful example to show how sometimes you want a rigid joints and sometimes you want flexible joints. So this one is kind of a fixed hinge there, and of course the motor shaft is also fixed. But that means that it's actually better to have rose bearings with a bit of flexibility at both ends of the crank, just so the bearings can't get stressed. Now the other thing about a simple crank mechanism like this, and one of the reasons I like cranks, is look how smooth the motion is. It sort of speeds up and slows down, speeds up and slows down. If I was to do that with a linear actuator, it would be more jerky, unless I programmed in some sort of ramping and stuff like that. But this does it very, very simply. So, for instance, an arm of a figure, it just looks much more natural as a motion with this slowing down and speeding up than the sort of jerky motion that you get from an actuator or a pneumatic cylinder. So you can get a lot of different sorts of movement out of a simple crank. This is like actual model I made, and also like the flowers in the water clock. The movement of this lever is almost vertical. And that's because this crank distance is much shorter than this long lever here, at the fixed point there. You get a completely different sort of motion if the lever connecting to the fixed point is only a bit bigger than the crank, which I'll try and show you now. So now you get a really big angle, like a sort of an extreme version of car windscreen wiper. Then it's also interesting adjusting the length of the connecting rod. If I get this one. So now this connecting link's only just longer than the crank, and what you get is what's called a quick return. So for almost half the rotation of the crank, the lever hardly moves, and then it moves rapidly over the second half. So there are these various sorts of motion that you can get from a simple crank. But then I've found that I can add things to cranks to make them even more versatile. One crank I like is what I call a locking crank. So this crank is connected to a door mechanism, and at the moment I could actually just pull the door open. Of course, in this instance it's slipping on a belt, so I could have connected it to the motor with gears or with a chain, but that puts a strain on the motor, so if somebody does pull it open, so it's not ideal. The simplest way to lock it is to get it to stop. Oh no, gone too far. Get it to stop precisely over the centre of the crank, because then there's no turning force. It doesn't want to turn either way. But as I just showed, it's quite difficult to get it to stop in exactly the right position. So I've actually had more success by adding a physical stop. So if I put this in here, now when I lock it that way, it goes slightly over centre and is now up against this physical stop. So now if I try and turn it, there's no way that the crank can turn. The only way to open the door is to reverse the motor, and then it opens perfectly easily. And you can have a really tiny motor, really low powered thing, but it'll still be locked very securely. So I used this in iZombie for the device that snatches your phone. I wanted the trapdoor to be locked until the right moment when it opens to gobble your phone up.
Their power keeps increasing. To ensure your continued rehabilitation, we have, free of charge, confiscated your phone for 3 hours.
So this is what I call my dropping crank. At the heart of it there's a conventional crank in there, which will just lift this top sort of platform, if you like, pushing it on the end of that pin. But there's also this arrangement on the side here that is actually a sort of lock. So when it gets up to the top, that lock snaps in, and it's now supported on the lock, not on the crank. You can see there's a gap under there now. But then behind here you can just see a yellow dot. That comes round and knocks into the lock, and that releases it and allows the platform to drop. And so you can put quite a heavy weight on here. In fact, I could stand on this. I've done that many times before. I've used this in the seats of my photo booths and in one or two other things as well. There are simpler ways of getting a sudden motion out of a crank, but this one is much the best, particularly for large loads. Single cranks are easy to make, but multiple ones, like on a car crankshaft, are really hard. So I generally try to avoid using them. So the only time I've used a multiple cranks was on this sign I made for the pier. So it's just a solar panel connected directly to the motor at the end, and to make the letters move in a wave shape, they're all on a crankshaft, and each crank is offset by about 45 degrees from the one before. Well, the first time I'd made it was a bit of a disaster. I didn't manage to get the crankshaft completely straight, and I used Delrin for the bearings, which for some reason swelled up, either with moisture or the heat. So I took it home, rebuilt it, and this one's much better. I split the crankshaft into separate sections and replaced the Delrin with Tufnell. It's a bit of a squeaky old thing at the moment. I need to get that up there and oil it really, but other than that it's worked okay ever since. This is the jig I'm built to make the segments of the crank. So these are two side pieces for the crank, and this is the pin that's going to go through the middle. And for temporarily I made a sort of spacer that goes through like that. Oops. So then these go under there into the jig, and then the shaft, I push that through on top like that, and then I can clamp the that way up, the shaft to the bottom of the angle to keep it accurately in line, and also I can clamp the other end of the crank down the bottom here. So that looks quite good. So now I can weld up the sides to the shaft and to the crank pin. So now it's all welded. Need to leave it clamped up until it cools. But then I'm being a bit impatient here. I can now put it in the vise. So the last thing I need to do is to cut off the centre, cut through the centre of the shaft. I'm going to put it in the lathe to see how concentric it is. Well, it's not brilliant, but it's interesting actually. I realise one of the reasons I've had trouble making these multiple cranks is that I'm making the sides too thin. The heat of the weld, even though I've clamped it, it can actually bend with knocking it not very hard. I should have used at least 6mm, if not 8mm flat for the sides, and then I think it would have worked a lot better. Anyway, that's how I did the ones for the solar sign on the pier. For more complicated movements there are cams. Some people get really clever at using cams and have done some amazing things with them. So a couple of things I find useful with cams. If the cam's at all complicated, it's very hard to get it right first time. So I like to make a rough version out of hardboard or aluminium that's easy to chop and change. So for instance, if I wanted to make that curve a little bit gentler, that's quite easy to do. It's just sand it down a bit. And I could make it even gentler still by cutting it a bit more. And then I can add to it. I tend to just use super glue and an activator, and I've actually added a little extra chunk here because I wasn't happy with that one. So you can go backwards and forwards until you get the cam the shape you want, and then you can make it in a better material. The other thing that I find useful with cams is to try and always use a ball race as the cam follower. I'm just using 2 here because they're rather skinny. And then this should make the motion a lot, reduces the friction and makes the motion smoother. For small cams, I find these tiny little 3mm roller bearings very useful. I used to use them with 3mm cap-headed screws as the cam follower. I think the outer diameter is 6.5mm. This is the next size up. This is the 4mm one, which I think is 7mm or 8mm. But the reason that I don't use cams very often is that there are lots of other ways of getting a more complex movement. I can get more complicated motions just with a simple crank by adding position switches. These switches send signals back to my PLC or to a microcontroller, so the actual movement is controlled by software. In some ways this is great because it's very flexible. The crank can do different actions at different points in a cycle, and it also saves space because if you think of it, you've got the whole of the throw of the crank as opposed to a cam which would just be sort of probably a quarter of that. Countering that though, a cam motion can be more subtle and gentle. There are advantages in both. Another way to produce more complicated motion, of course, is to use a stepper motor. In this case, you don't need any switches. What's happening is that the PLC is sending a series of very rapid pulses to the motor. Each one makes it move one step. In this case, I'm sending one every 50th of a second, and there are 400 steps to make for one revolution of the motor. This is a more modern way of solving the problem, but they all have their different strengths and weaknesses, and choosing between a cam, a stepper and the position switches can be tricky. Personally, I use the position switches more than the others, but that's largely because what I have most experience of, so it's quick and predictable for my purposes. I rescued all these complicated old mechanisms from the scrapyard, mostly some time ago. There's a clocking in clock here, another one there. This is from a petrol pump, a forecourt petrol pump when they were still mechanical. This is some sort of industrial printing machine. There's some aircraft instruments down there, and some of the others at the front there are just complete mysteries. Made in the 50s mainly, I think, when I was a kid, but now obviously all completely obsolete, replaced by solid state digital. That's a lot cheaper to make and probably mostly more reliable too. I've really enjoyed witnessing over my career the gradual change from analog and mechanical to solid state digital. I'm reasonably comfortable with both and enjoy picking and choosing the best of both worlds, if you like. So while it would be possible to make screen-based digital versions of my arcade machines, I don't think people would put money in them. They're much more unusual and interesting by being mechanical. What I do really is to sprinkle a bit of digital sort of intelligence on top of machines that are basically electromechanical. And it's territory that's largely unexplored, but just suits me perfectly. And while making mechanisms like this would be completely pointless today, I still find I can't resist making my own complicated mechanisms sometimes. But rather than going down that wormhole, I thought it might be more useful to end this video with two additional simple mechanisms that I particularly like. One motion that I often seem to need on my machines is to flip a scene or part of a scene round by 180 degrees. And you can't do that with a simple crank. The maximum angle you can get is surprisingly small. I was just measuring it. It's actually only, well, it's a bit more than that. It's about 110 or 120 absolute maximum. So if you want a 180 degree turn, you've got to do something different, and I've tried various ways of doing it. This was the most satisfying mechanism and the one that's had the most use. It's triggered every time anyone comes onto the pier. So about 15 years ago, the pier commissioned me to make a no smoking sign to alert people as they walked onto the pier. And for this to work, obviously, all the faces has to flip perfectly by 180 degrees. So the way this works is for this crank around the motor to move these pulleys by about 90 degrees. So these pulleys are connected to pulleys that are half the size up at the top here on the pivot of the faces. So they move twice the angle, but just that by itself wouldn't be enough to give a perfect 180 degrees, because these are all quite loose, these cords. What really makes it work, the difference, is these counterweights. So at the moment the counterweights are resting against the stop, and when it moves, once they've overbalanced the top, they then just sort of want to carry on till they reach the other stop, and it's that that makes them move so nicely 180 degrees. And I don't know how many hundreds of thousands of times this thing's been used. It's amazing it still works, really. When I was starting pirate practice, I obviously had to connect the bouncing motion to make the boats go up. Well, on this very rough first prototype, I hadn't made any boats, so it's just bits of paper going up. But very early on, I found that I could do it with capstans. I've never used a capstan before. So I've made this model to show roughly how it worked. So it has a spring, and then the cord wraps around the capstan a few times, And then when you go down on your boats, it pulls the cord and pulls capstans round. But when you go up, the rope slackens off, and so the capstan doesn't turn. So you get this nice gentle motion of it only turning in the one direction. Well, when I got it on the pier, it worked perfectly in the workshop, but when I got it on the pier, I found that very often one boat would be going further than the other boat, and sometimes one boat wouldn't be moving at all. So I was forever adjusting these springs, and this went on and on and on, and I just couldn't see what could be wrong with such a wonderfully simple mechanism. During COVID lockdown, I had more time and found out quite a lot more about capstans. Of course, traditionally you have them on ships. So here, you're going to imagine my vice is the ship. You throw out a mooring line to the dock, then you wrap the rope around the capstan a few times. I found this worked best with 4 wraps. Then you get the capstan motor going. So it's not like I was using the capstan. But now if I apply a little bit of pull here, it's extraordinary what happens. It's enough to move this massive vice, or rather ship, across to the dock. So what they're doing really, it's a torque amplifier capstan. So the small amount of pull that I'm putting here is translated to a much bigger pull, pulling the vice across. So finally, understanding capstans a little bit better, I got to the bottom of the problem. The thing was that the cord wasn't going directly to the bouncing mechanism. To get there, it had to go via a couple of pulleys. So the path was sort of roughly like that. So what happens is that it actually behaves completely differently. And the reason for this is that although the pulleys feel completely free, there's a small amount of friction. And that means that the cord never goes completely slack around the capstan. So like with the vice, it's as if I'm still holding on quite tight. So if I remove the pulleys, it goes back to working as it did before. So the solution was simple. I just got rid of the pulleys and I made a mechanical rigid linkage instead with bell cranks and things. It wasn't easy to get it right. I had some teething problems with it, but I think finally the boats are now moving equally and make it a much better game. But I'm glad I persevered. I think this is a good example where a mechanical linkage has advantages. You really feel connected to the boat. The bouncing is so completely in time with the movement of the boats. It would be difficult to make it quite so intuitive to do it electronically with servos and stuff. This is sort of called more magical, really.
Good work. Now it's showtime. Where is the boss? Where is the boss?
Oh, is that a Kalashnikov? Do you like a cocktail?
Where is the money? Don't hurt me. Take her. Open the safe. Open the safe. Son, I admire your business model. We should work together. Boys, time to go.
So though it took a while, I definitely think that capstans were worth the struggle. Anyway, that's the end of this video. I hope you found something useful and enjoy making your own linkages and mechanisms. Bye.